All right, starting into a new chapter, we're entering into chemical bonding 1, the Lewis model. Any guesses about what's coming up after this chapter? If this is chemical bonding 1, what do we think is coming next? It's chemical bonding 2. So just keep that in mind. This isn't all the chemical bonding that we're going to do. So we're going to focus in on the Lewis model first. Bonding models have been around for a long time, relatively longer than most of us, probably all of us. In 1989, the structure of HIV protease was determined. It's a protein that's synthesized by the HIV virus. And they were able to design several molecules that could disable that HIV protease by binding to the active site. And I apparently forgot to unlock the door. Compared to modern modeling and bonding models, these older models were probably somewhat primitive compared to like supercomputer computing models. But they still had bonding theories that they were able to use to simulate shapes of different drug molecules and determine how they would interact based on the thing that they were trying to target. So they took a particular protein, they created a model of it, and they said, what kind of chemicals can we throw at that active site where we know that it reacts with some part of our body. We can do this now with a lot more power. You can run hundreds of thousands of different chemicals in simulations to compare, how are all these different possible drugs going to interact with the active site of whatever thing we're trying to target. And you can narrow that down to maybe 100 different molecules, run more follow-up simulations with those, or even have people make them or order them, and then go and run them and screen them against the thing that you're trying to target. We're not going to be doing any of that, because that's way beyond this class. But the general idea behind bonding molecules, or bonding models, is that these theories can help explain how our atoms are bonded together, which can inform how our models, how our molecules, our atoms, our things, our chemicals are shaped. And the shape can also, in turn, determine how they behave. So for example, this can help answer questions like, why are some molecules stable and others not so stable? I may have mentioned, but I probably haven't mentioned yet in this class, that sometimes when we're putting together structures for molecules, people want to put them in little triangles. Triangles tend to explode. They're not very stable. And bonding models can help explain why triangles are not very stable in chemical molecules. They can also help us predict the shape of the molecules, and shape often determines some of our chemical and physical properties. There are also different bonding models. We are going to learn very basic bonding models. So there's a big trade-off. We don't have nearly as much predictive power or complexity, but we don't need a supercomputer to do it, and we can learn how to do it basically in a day or a couple of days. So the model that we're going to be learning is the Lewis model. If you've taken Chem 20 or Chem 10, you've probably already learned the Lewis model, and so some of this is going to be review. So in the Lewis model, valence electrons are represented as dots. Who remembers what valence electrons are? Yeah, they're the electrons in the outside shell, in the highest n level shell. And so our Lewis electron dot structures depict molecules. We are going to start off with drawing individual atom symbols. It's a very simple model. It can give us the shape of molecules or help us get to the shape of molecules, and it can also predict if a molecule is likely to be stable. We'll also learn some tools that will help us figure out what's the best configuration. Sometimes there's multiple ways that you can put things together, and so how do we weigh which option we have? For example, something with this sort of a skeletal structure as a starting point versus this as a skeletal structure. One of these two is going to exist, and the other is unlikely to exist. So we'll learn tools for how to put this together, how to figure out which of those two is more likely to be stable. Before we get there, let's talk about some chemical bonds. So chemical bonds, bonds between atoms, form because they lower the potential energy between the charged particles that compose the atom. So it reduces our potential energy with our electrons, with our protons. As a couple of atoms approach each other, two atoms approach each other, there's some interactions that are going on. The electrons are going to repel each other. The nuclei are going to repel each other. Remember that our electrons are negatively charged. Our nuclei are protons and neutrons, and our protons are positively charged. So those positive charges are going to repel each other. However, our electrons and our nuclei are attracted to each other. Since our electrons are negatively charged, our nuclei, our nucleuses, are positively charged. A bond will form if it results in a net reduction in energy. Lower energy is more stable. Just generally, if we're lowering our energy, we're increasing stability. Kind of settles into that lower energy state. So one of our types of bonds that we can form is ionic bonds. Ionic bonds exist between metals and nonmetals, or cations and anions. Metals tend to have low ionization energy. They tend to lose electrons to form cations. A low ionization energy, remember ionization energy is the energy required to remove an electron from an atom in the gas state. So what we're saying here is that it's easy to remove an electron. So metals like to lose electrons, and they form cations, which are positive. Nonmetals, on the other hand, have negative electron affinities, high ionization energies, and they like to pick up or gain electrons. And they form anions when they pick up electrons. So if a metal meets a nonmetal and the mood is right, then the metal is going to transfer electrons to the nonmetal. The result is that we have oppositely charged ions. We've got a cation and an anion, and they're attracted to each other because opposites attract. We also have covalent bonds. Covalent bonds are formed between nonmetals. And these are shared electrons. Ionic bonds, there's a transfer of electrons. In our covalent bonds, the co meaning that they're sharing, and the valent meaning we're talking about the valence electrons. So nonmetals share electrons. The shared electrons interact with both nuclei. So the two atoms that are involved in the bond, they both get some shared time with the electrons. The most stable arrangement, the most stable place to keep your electrons between two atoms is, as it turns out, between two atoms. So we've got a couple of options down here. Our positive charges here are our nuclei, and then we've got our electron or electrons that we're sharing in our bond. as you might imagine, keeping your electrons out off to the side is not very stable. They're further away from both of the positive nuclei. It's not a very great place to keep your electrons. It's also not a very great place to keep your electrons way over closer to one positively charged center, because we've got a really long distance here. The most stable and lowest potential energy place is right between your two nuclei. Just like if you and a friend are trying to carry something, you're probably not going to both stand on the same side. Like if it's a large table, you're not going to both stand on the same side of the big table and try to carry it up in front of yourselves, and like both of you are walking forward. One of you will pick up one end, the other will pick up the other end, and one of you gets to walk backwards, presumably whoever's not wearing flip-flops. Or if you're both wearing flip-flops, maybe you just walk sideways. So this is the most stable place to keep our electrons, and we get the attractive force between both the nuclei and the electron and the other nuclei and the electron, or electrons. We also have metallic bonding, which, as you could probably guess, occurs when we've got metals. And our simplest model for metallic bonding is the electron C model. Basically, we've got a bunch of positively charged metal centers that are all just kind of sitting next to each other. And we've got electrons that are floating around and just kind of loosely, freely shared between our metal centers. So electrons flow freely and are shared. So in contrast to our ionic bonds, where the electrons are transferred over and just held in one place, also in contrast to our covalent bonds, where they're shared evenly, but they're kind of stuck between our nuclei, our metallic bonds are the communists of bonding. All the electrons just kind of get shared. It's or the hippies of bonding. It's all free electrons. They're all just floating around, being shared equally. They don't really belong to anyone. So they're delocalized over the entire metal, and the positive nuclei just kind of sit in the sea of negatively charged electrons. The free-flowing nature of the electrons also would explain why metals are good, like copper is good for conducting electricity. If the electrons can flow freely, then that means that you should be able to get electricity to flow through there pretty well. Okay, back to our Lewis structures, our Lewis theory. So we represent our valence electrons, our outside electrons, with dots. Our valence electrons are the most important when we're talking about chemical bonding. These are in our outermost principal energy level, our highest N number. And because they're on the outside, they're the most loosely held. They're the first ones that are going to come off, or the first ones that are going to be able to interact because they're on the outside. In a Lewis symbol, or a Lewis dot structure, our valence electrons are shown as dots around the element symbol. So for example, a Lewis structure for oxygen, we're going to have our symbol for oxygen, and then the valence electrons show up as dots around our symbol. How many valence electrons does oxygen have? 6. It's in the 6A group, so it has 6 valence electrons. And we're going to place them, there's basically 4 sides. So if we just put in an X to show our symbol, we've got basically 4 sides that we can place our electrons on. We can get 2 electrons per side as our maximum. We're going to place them individually first, and then we'll pair them up after we're done. So 1, 2, 3, 4. We've got 6 to place, so we'll have to double up 2 of them. It doesn't matter where you double them up. And if you know that you're going to be adding multiple on, if you know you're going to be adding 5, 6, 7, 8, you can go in with double dots initially. Just make sure that you don't end up with unpaired electrons or empty sides. So you could also have both the pairs on the top and the left. You could have them on the bottom and the right. You could have them on the top and the bottom. It doesn't matter where they are, just as long as you've got the correct number of dots in there. So we place our dots, we get a maximum of 2 per side. And this is just a simple way for us to visualize our valence electrons, keeping them to a maximum of 2 per side. If we have atoms with 8 valence electrons, we call that an octet. So 8 valence electrons is an octet. Oct being our prefix for 8, like in octopus or octagon. And these are particularly stable. Octet is generally the goal for all of our atoms. All of our atoms want to have an octet, except for things like helium, which is a duet of 2 electrons. Hydrogen also likes to have a duet of electrons. So it's happy with just 2 electrons. So generally, 8 valence electrons is the goal. For each/every atom. With the exceptions of hydrogen and helium and lithium. Why do hydrogen and helium, why are those happy with 2 valence electrons? Any ideas? If they have 2 valence electrons, what does that mean for their electron configuration? Hydrogen has the electron configure 1s1. If it has 2 electrons, then it would be 1s2. And this is a full outer shell. For everything that's bigger than hydrogen and helium and lithium, things like oxygen, oxygen is going to be 1s2, 2s2, 2p4. If it has 8 valence electrons, then it would be 2p6, which would give it a full valence shell. So the reason that octet is the goal, or a duet in the case of small things like hydrogen and helium, is because we want a full valence shell for our electron configuration. It's easier, though, just to say we want 8 valence electrons. But that's the kind of behind the scenes. Questions so far? Great. Let's draw Lewis structures for potassium and chlorine. So potassium, K, chlorine, Cl. How many valence electrons does potassium have? 1. It's in group 1, so it has 1 valence electron. Chlorine has how many? That has 7, because it's in group 7A or 17. So we draw on 7 dots. And when these two bond, since it's ionic, this one electron is going to transfer over to the chlorine. And what that does for our valence shell, here's our full electron configuration for potassium. Notice we've got this 4s1. When we take off that 4s1 and make it 4s0, we reveal a full octet in the previous level. So stripping away all of our valence electrons is another way of getting to a full octet. So we don't draw anything in, we just leave it blank, but it secretly has a full octet. And then the way that we would write this after we've done the electron transfer, we've had K+, and we would have our chloride ion. I'll retain that blue color. And we need to have brackets around our chloride, and we put the negative charge up outside of the brackets. The reason that we put in the brackets is so that we know all of these electrons only belong to the chlorine. So brackets show that the electrons are only on chlorine. Potassium is not sharing in any of those valence electrons. One of the ways that we do other bonds, or one of the ways we can do other bonds, is by drawing 2 dots between 2 symbols, and that would mean that they're sharing those 2 electrons. So we have to draw the brackets to make it clear those only belong to the chlorine, the chloride ion that we have here. And we also do brackets for polyatomic ions as well. So if we had a group, we would do the brackets around the whole thing, charge in the top right corner, to show that that whole thing has whatever that charge is. Okay, so we can use Lewis symbols to predict compounds for ionic compounds, formulas for ionic compounds. It's kind of slow. We're generally not going to do this because we've got the swap and drop method where we take the charge, right, and rewrite it as the subscript of the other thing, and that's just way faster. This gets us to the same result. We're kind of just doing this to show you that it works. So let's look at magnesium and nitrogen. How many valence electrons do magnesium and nitrogen have? Magnesium is going to have 2. Nitrogen is going to have 5. Magnesium is a metal, nitrogen's a nonmetal, so when these bond, they're going to form ionic bonds. And in ionic bonds, we transfer electrons. So we can transfer electrons from our magnesium. I'll just go ahead and do full arrows. We can transfer them from the magnesium to the nitrogen. And this would turn into Mg2+. We lost 2 electrons. And we would have our nitrogen that has now picked up 2 electrons. Our magnesium, since it lost its outer shell, right, it lost its outer shell. So this secretly reveals underneath, since magnesium is in row 3, it's actually got neon electron configuration. So it's got a full octet. So magnesium is happy here. So we'll put a check mark on magnesium. It's got its full octet. Is nitrogen happy? Does it have its full octet? It doesn't, right? We've got 3 sides that have 2 dots We've got one side that only has one dot, so we need one more electron. Where could we get another electron from? Toys R Us? Probably not. But if we've got one magnesium around, I think it's probably pretty safe to say there's probably another magnesium around too. So we can get it from another magnesium. This magnesium is also going to have 2 valence electrons. And so the second magnesium can give an electron to our nitrogen. And when it does that, now our nitrogen has a 3-. It's got a full octet. So all's well and good. Except this other magnesium has 1 electron in its valence shell. It doesn't like to have 1 electron in its valence shell. It wants to have either 0, which reveals the octet underneath, or it wants to have 8. Where can we get rid of this 1 electron? Where can we send it? Another nitrogen. And this other nitrogen is going to have, you guessed it, 5 valence electrons. So let's transfer that other last electron from our magnesium. Our magnesium now a 2+, so it's got its full octet. Our nitrogen also got its full octet. Is our second nitrogen happy? Is it content? Does it have what it wants? It does not. It does not have complete and total world domination. It doesn't even have a full octet. It needs a couple more electrons. Where could we get some more electrons from? Another magnesium. So a third magnesium enters the picture, and it has 2 valence electrons. It can donate both of these valence electrons to the nitrogen to fill out the valence shell for the nitrogen. Our magnesium's now a 2+. Our nitrogen's a 3-. Is everyone happy? And by everyone, I don't mean all of us. I mean, are all of our atoms happy? Yeah, all of our atoms are happy. They got their full octets. And hopefully we're happy too, or at least close enough. We'll get through it. Okay, so we got all of our full octets. How many magnesiums, how many nitrogens did we use? We used 3 magnesiums. So this predicts Mg3. We used 2 nitrogens, so Mg3 too. This is the structure predicted by our Lewis, or the formula predicted by Lewis theory. And this is sort of what we're doing when we do that swap and drop. So if we do it over here in red, magnesium likes to form 2+, nitrogen likes to form a 3-. We swap and drop or crisscross, we get Mg3 N2. We didn't have to draw any electrons, we didn't have to draw any arrows. Well, we drew 2 arrows, but we didn't have to. And it was a whole lot faster. And this is sort of the shortcut for what we've done here with Lewis theory. We're sort of doing the same thing, it's just that this is a lot more drawing and work. So that's kind of just to show you that it works. Okay, some extra information you probably didn't cover if you took Chem 10 or Chem 20. Lattice energy. So as it turns out, the formation of ionic compounds is usually quite exothermic. What does exothermic mean? It has to do with energy. Is it energy gained or released? It is energy released. So there's a lot of energy that's released when we form ionic compounds, generally. So for example, for the formation of sodium chloride, our standard enthalpy of formation is -411 kilojoules per mole. which is a relatively large number. And just as a reminder, that 1/2 in front of our Cl2 is because it's a standard enthalpy of formation. That's the only time that we see fractional coefficients. If we look at the ionization energies and the electron affinities, it doesn't entirely explain this. So for example, the ionization energy for the sodium, for it losing that 1 electron, you'd have to put in about 500 kilojoules per mole. The electron affinity for chloride, it would release about 350 kilojoules per mole. And so the net effect is we expect that the transfer of an electron is going to absorb 147 kilojoules per mole. This is very different, this expectation, from reality, because we have the reality up here, this negative 411. So how do we explain the difference between these two numbers? And the way that we explain it is lattice energy. So we're making the assumption that these two are just kind of transferring the electrons and maybe they're linking up. In reality, when ionic compounds form, they form a lattice. A trellis would be an example, sort of a lattice. The things that vines climb on where they've got the crossbars. If you think of all those intersection points of those crossbars being ions, that's our lattice. We've got a bunch of vertical lines. We've got a bunch of horizontal lines, like you might see if you're walking into somebody's house and they've got the nice like floral archway with vines on it. Right, some of these intersection points, maybe on just graph paper, some of those are going to be one ion, the other intersection points would be the other ions, but unlike a trellis, this occurs in 3 dimensions. So we would have this set up, the green line's just our graph paper, we'd have this set up with positive and negative charges, we'd have another set alternating behind it, and another behind that, and another behind that. So we've got this 3-dimensional array of all these different ions stacked up. And that's what the lattice part of the lattice energy is. We've got a 3-dimensional arrangement, alternating positive and negative charges. And our potential energy is lowered when our opposite charges come together. So the potential energy is lowered, which means that it's more stable. Because we've got that alternating array of positive and negative charges, they're really nice and cozy with, if we're the positive charge, we're really nice and cozy with all the negative charges around us. We're really nicely seated. In order to get rid of that energy, in order to lower that potential energy, it has to go somewhere. It doesn't just get destroyed, and so it gets released as heat. This is sort of like if you or an animal or a child, it's time for bed, you've got a lot of energy, dog has a lot of energy, child has a lot of energy. How do you get rid of that energy? You don't just lay down and magically fall asleep. You go for a walk, you go do some chores, you go for a run, you take your dog for a walk. You have your toddler run circles or go on the treadmill and play games, maybe not playing games on the treadmill. You do something to get the energy out, and as it turns out, atoms and ions can't do that, so they just release it as heat. This is sort of like when we were talking about quantum mechanics, or electrons dropping to lower energy levels, they released it as light, but this time we're releasing it as heat. So that's where the energy comes from. It's because of this lowering of potential energy. It's not because of them wanting to lose an electron or gain an electron. Like as we saw here earlier, right? It actually absorbs energy. It's because of the lattice, the alternating positive and negative charges. And here we've got This image, which is very funny to me for some reason because it's reminiscent of many memes. So we've got all these gas ions coalescing, positive, negative charges, and they settle into this really tight array, lattice, where we've got alternating positive, negative, positive, negative, positive, negative in 3 dimensions. And the amount of energy that's released is our lattice energy. And there's a name for a way that we can calculate lattice energy, and it's the Born-Haber cycle. So the Born-Haber cycle is a hypothetical series of steps. It represents the formation of the ionic compound from its constituent elements. And it's basically just Hess's law. So we're going to use Hess's law to calculate change in enthalpy, standard, and formation, all that stuff in there. But we're going to compare to the actual calculate standard change of enthalpy of formation for ionic compound. We'll see these steps on the next slide, so it'll be less confusing then. And then we're going to compare to the actual standard enthalpy change of formation. And the difference is the lattice energy. Okay, so here's what that Born-Haber cycle looks like. Okay, let me zoom. All right, we're zooming. So our starting point is here. We've got sodium as a solid. We've got 1/2 Cl2 as a gas. We have to do this as a gas. So we have to take our sodium from a solid, turn it into a gas. That requires energy being put in. That's our delta H, standard delta H for our first step. And then we have to take, so we're going from a solid to a gas. In our next step, we're going from Cl2 to Cl. And that also involves putting energy in. And then we have to ionize our gaseous sodium. So we're going from sodium to sodium plus, sodium ion. We're going then from chlorine, atomic chlorine to chloride. And then we would expect that these two things would just latch together, and that would be our endpoint. But we know that our sodium chloride is actually this distance down. So this is where we would expect NaCl to be. Expected delta H for sodium chloride. This is our actual delta H for sodium chloride. And this difference is our lattice energy. So we do Hess's law to add up all of these little steps. We compare it with our actual enthalpy of formation. The difference between the predicted and the actual is the lattice energy. In this case, it's a large number. And we can make some general claims and predictions and trends about lattice energy. Do we have questions so far before we get to the trends? We basically have two trends. I don't think they're particularly complicated. And they are related to Coulomb's law. So we've got a trend for ion size. For ion size, if we look at some metal chlorides, so this is different metal ions paired with chloride ions, we can see that lithium chloride has the highest lattice energy, cesium chloride has the lowest lattice energy, and if we compare these pairings, lithium chloride, sodium, potassium, cesium chloride, we can see that the distance between our nuclei is different. Right, lithium chloride has the shortest distance, cesium chloride has the longest, and this explains why our lattice energy changes. Our lattice energy is really high for lithium chloride because our nuclei, or our ions, can get really close together. Coulomb's law tells us that energy is proportional to 1 over the radius. So it's proportional to the inverse, or inversely proportional to radius or distance between our charges. So as radius decreases, as radius goes down, energy, stabilization, goes up or gets bigger. So the closer our ions can get to each other, the stronger the energy is going to be, thanks to Coulomb's law, and the greater the stabilization will be. So we expect higher lattice energy for smaller ion pairs. Our other trend is for ion charge. So if we look at sodium fluoride versus calcium oxide, our lattice energy difference is dramatic. So our sodium fluoride has a lattice energy of 910, quite stable. Our calcium oxide has a lattice energy that's almost 4 times as big, almost 4 times that size. And if we look at ionic size, they're right about the same. So ionic size doesn't explain this difference. What does explain this difference is the magnitude of the charges. Coulomb's law also has a charge 1 and a charge 2 in it, and the charge and the energy, or the charges and the energy, are proportional. So as charge increases, the energy increases. And by increases, I'm talking about the magnitude. It's more negative. If we compare, right, we've got a +1, -1 for our charges, and I'm annoyed that I wrote them that way. We've got a 1+, we've got a 1-. For calcium oxide, we've got a 2+ and a 2-. We doubled both of our charges, our Q1 and our Q2. So for our energy for a sodium fluoride was K times the charges, 1 plus times 1 minus. Then it makes sense that our energy for our calcium oxide would be a similar K value, but 2 plus times 2 minus, so it would be -1, whatever this K value is, for our sodium fluoride. And for our calcium oxide, it would be about 4 times because we doubled both of the charges. So it makes sense that our lattice energy is about 4 times because of the way that our charges changed. If we wanted to, we could put all the numbers in with Coulomb's law and actually do the math. I don't want to. Questions about either of our two trends? Real fast, hopefully relatively easy. Okay, so our trends in lattice energies. Lattice energies become less exothermic with increasing ionic radius, or more exothermic with smaller radius. They also become more exothermic with increasing ionic charge. And both of these are based on Coulomb's law. In order for you to predict the radius, you would either have to know the radius, be given the radius, or you would have to make a guess based on the size, the atomic size of your ions. So that would also require you knowing the trends with the periodic table for atomic size or ionic size. Okay, let's make some guesses. Arrange the following in order of magnitude of lattice energy, increasing magnitude. So we've got lithium bromide, there's lithium, there's bromine, we've got potassium iodide here in green, and then calcium oxide with the blue here. Let's take a little bit of time to see if you can figure out which of those is going to be the most exothermic, which will be the least exothermic, which will be the middleist exothermic. And chit-chat and compare with your neighbors. All right. We've got 3 different ionic compounds. We've got 2 trends. We've got to use our 2 trends to figure out our ordering for these 3 ionic compounds. What's one of our trends? What's something that affects lattice energy? Radius. What's our other trend? Charge. How do these trends affect the magnitude of our lattice energy? When radius does what happens to the magnitude of our lattice energy? Does our lattice energy increase when radius increases? It's the opposite. When radius decreases, energy increases in magnitude. So the closer our ions are together, the higher the lattice energy is going to be. With charge, as charge increases, energy also increases. And as we saw in the previous couple of slides, charge is a much bigger factor. Much bigger factor. Because when we double one of the charges, we're doubling the energy. In order for us to double the atomic radius or cut the ionic radius in half, we'd have to have a drastic change in our atomic size, which I don't think is likely that we're going to see. So generally, charge is going to be a much bigger factor. So let's look at our different ionic compounds. What charges do we have for these? The lithium bromide, right? Lithium is over in our first column. It's going to be a 1+ charge. For potassium iodide, potassium is going to have a 1+ charge. And bromine and iodine are each going to have a 1- charge. So we've got 1+, 1-, 1+, 1-. For calcium and oxygen, we saw those earlier. It's 2+, 2-. So based on charge, which one is definitely the highest? Which one has the biggest charge times charge? Calcium oxide. So based on charge, calcium oxide is highest. And then we are not sure about lithium bromide and potassium iodide based on charge. But we have our other trend, which says that as the radius decreases, as they get closer together, our energy increases. So we have to compare lithium bromide and potassium iodide. Lithium bromide's here in the red. Potassium iodide is here in the green. Which one of these has bigger molecules? Is it lithium bromide or potassium iodide? Which one's going to have bigger atoms? How does atomic size change as we go up or down the periodic table? How about as we go down the periodic table, how does it change? How does size change? Do they get bigger or do they get smaller? They get bigger. Right, and so for our green one, potassium and iodine, those are both lower, so those are both bigger. So for radius, not H, K, I has a bigger radius than lithium bromide, since K and I are bigger than lithium and bromine. So we're going to have a bigger radius for potassium iodide. A bigger radius would mean lower energy. Smaller radius, lithium bromide. Smaller radius means bigger energy. So lithium bromide is going to have the higher energy. For comparing those two. Do we have questions about any of those steps? Okay. So that's some comparison of lattice energy. We've talked about ionic bonding a little bit, a decent amount, right? We're transferring electrons from our metal to our nonmetal. Does our ionic bonding model explain the properties of ionic compounds? Well, we have high melting point for ionic compounds, and that's because we've got our ions in this lattice, this positive-negative alternating array. And so they're very well stabilized. That's part of the reason that they're so exothermic when we put them together. We've got non-directional bonds. They're bonded in every single which way and direction. So a high melting point makes sense because there's bonds all over the place and they're strong bonds. We also have non-conductivity of ionic solids. So if you've ever tried to conduct electricity with just like salt, just salt, dry salt, it won't work because our ions are fixed in place. They're fixed in place. They can't move to conduct electricity. However, solutions of ionic compounds, if we separate it out from a solid into a solution, they're no longer stuck in that lattice, and they can move whichever way the electricity needs to flow. So that's why solutions of salt water and other strong electrolytes conduct electricity, and you can run electricity through those solutions. Also why it's dangerous to run electrical appliances in the bathtub, because you could electrocute yourself. So yes, our ionic bonding model does explain these properties. Okay, so that's all our ionic stuff. On to the more relevant stuff, the stuff we're going to be spending more time on, which is covalent bonds. So Lewis structures show molecular compounds. Molecular compounds, remember, just being nonmetals. They show these as neighboring atoms that share electrons. That's the co in covalent bonds. They share electrons in order to attain octets or duets in the case of hydrogen. We can use Lewis structure to show bonding in H2O and Cl2. The thing that we need to start with is placing our atoms. So for H2O, generally we like to have things be nice and symmetrical. If we look at our Lewis dot structures for each of these individually, our hydrogens have 1 electron. Our oxygen has 6 valence electrons. So our Lewis structures would look something like this. And we can share some of these pairs of electrons. So hydrogen can share 1 electron with oxygen. Oxygen shares 1 of its electrons with hydrogen, and the same thing on the other side. And we can rewrite this as H with the 2 dots in the middle, oxygen, 2 more dots, the other hydrogen, and don't forget our lone pairs. For Cl2, we've got 2 chlorines. They're each going to have 7 valence electrons. And these can also share 1 electron to form Cl2. So we also would like to identify bonding pairs. Our bonding pairs are the ones that I'm circling here. They're the ones that are between atoms. Our bonding pairs are shared. They count for both octets. So for our H2O, the hydrogen on the left, the hydrogen on the right, they each are next to one of those bonds. So they have 2 valence electrons towards their count. So they've got their duets. Our oxygen in the middle has those 2 pairs on the sides, the 2 bonds. It also has the 2 lone pairs, the top and the bottom. these ones. So our oxygen has 2 bonds for 4 electrons total, because 2 electrons each, and 2 lone pairs, four electrons total, for a full octet. We could also just count, right, the number of dots that we have around our oxygen, which is 8. And the same idea applies for our chlorines. They've got 3 lone pairs each, and then another bonding pair in the single bond. We are often, though, going to show this instead as the CLs next to each other and replace the bond with a line so that we've got fewer dots. So this straight line represents 2 electrons. That's typically how we're going to show bonding pairs. But because we do have this other option, right, where these are shared electrons, that's why we've got to put brackets around our ionic charges so that we're making sure that they're not being shown as shared. Questions? If you want a review, or if you never learned Lewis structures and you'd like a more in-depth review, I've got videos in my Chem 20 series for Lewis structures, like from the ground up. Some of it will be review. 2 atoms can also share more than 1 electron pair. So for example, we can have a double bond in O2. So if we look at our oxygens by themselves, they're going to have 6 valence electrons. So they've each got 2 unpaired electrons. We can pair those electrons to make bonds. Boom, bam, bop. And this turns into, there's 2 options for how to write this. We've got the dot method, which looks like this. These other lone pairs can go anywhere. I like to put them top and bottom. So this block in the middle is a double bond. The nice thing about showing them all as dots is that it's pretty clear, like it's easy to count up how many electrons are there. But this is exactly the same as if we draw it in as 2 lines instead. So the only tricky part about using the lines, which is more common, is that 2 lines equals 2 bonds. Each bond is 2 electrons. So that's also a double bond. Which is 2 sets of 2 electrons for a total of 4 electrons. And then if we look at the lone pairs, we've got 2 lone pairs as well. 2 lone pairs is 4 electrons. We can count the dots. All right, 1, 2, 3, 4, plus the 4 in the double bond. So each of these has a full octet. So 4 electrons in lone pairs, 4 electrons in the double bond. So that counts up to 8 electrons. The bonds count for both of the atoms' octet count. A similar thing happens in nitrogen, but nitrogen needs to share more electrons. So we can form 3 bonds. Which we could represent with 3 sets of dots, 3 colons. like that. Or more likely, with 3 lines. So that's a triple bond. So our triple bond has a total of 6 electrons in it. This counts towards each of the nitrogen's octets, and then they've got a lone pair as well. The lone pairs don't have to go on the outsides. They could be top and bottom. I just like the way it looks if they're on the outsides. Questions about any of these? Okay, so covalent bonding. Our Lewis model predicts the stability of H2O and H3O, which is unstable. So if we look at our Lewis structures for these, right, hydrogen comes in with 1. We've got our oxygen in the middle with 6. You don't have to necessarily write this down. So if we've got H2O, it would look like this. I'm going to copy this and duplicate it for adding another one. So H3O over here, unstable, H2O here, stable, because we can form these bonds. If we form these bonds, but for H3O, our oxygen already has an octet. So it's content. It doesn't want any more bonds. We could force it to have another bond. And then this would turn into this monstrosity. H, H, H. It would look like this. Our hydrogens are all happy, but we would be left with 3 more electrons on our oxygen. And now it has 9 valence electrons, which is not what it wants. Oxygen hates this. Full octet, good. Anything else, not good. I'm not going to do H3O plus and H2O2. H3O plus is the same as this one, just remove one of the electrons because the hydrogen here is coming in with just H plus, and so it just grabs this lone pair and it turns into a bond, and then the oxygen in the middle has its full octet. So it's this minus 1 electron, so that works because then oxygen has an octet, the hydrogens all have their duets. Unlike ionic bonds, covalent bonds are highly directional. They're only between two atoms. Each bond is only between 2 atoms. Covalent compounds contain individual molecules. Discrete here just meaning that they're like their own whole contained thing. Like each of us is a discrete human being. It's not like we're keeping things on the down low, although we probably are. It just means that we're self-contained. We're not like a big amalgamation of a bunch of human beings that all lumped into one abomination. So covalent compounds contain individual molecules, individual units of molecules, versus the array of positive and negative charges, the lattice that we get with ionic compounds. The weak forces that are between the molecules result in lower melting points. Any questions about any of all that? Okay, then we will stop for today.